When you picture a vehicle's engine, you likely see brute force, heavy steel, pumping pistons, and thousands of explosions per minute. But beneath that mechanical surface, modern engines operate as high-speed mathematicians. This is especially true for vehicles running on compressed natural gas, or CNG. It burns exceptionally clean and delivers serious power, but the fuel itself is volatile and deeply chaotic to control. To tame that volatility, rigid gears and fixed computer code fall short. The engine requires a control system that can continuously learn, adapt, and rewrite its own rules on the fly. This chart illustrates the first major hurdle: extreme pressure variance. A full CNG tank sits at a crushing 20,000 kilopascals, but by the time it's nearly empty, that pressure plummets to 5,000. Then there is the chemistry. Unlike liquid fuels, the concentration of convertible methane and CNG changes depending on the source. Every time you fill up, the chemical makeup of your fuel is slightly different. Finally, there's the physical reality of the hardware itself. Over years of driving, parts inevitably wear down, and seals can perish, allowing microscopic air leaks to develop. If engineers programmed an engine with a single, hard-coded set of instructions, these shifting variables would overwhelm it. The vehicle would stall at intersections, it would waste fuel, and eventually destroy its exhaust system. To keep the engine running, the central computer pursues a single baseline objective: finding the perfect ratio of air to fuel for every individual combustion event. Milliseconds before a spark plug fires, the system pulls in data from across the vehicle. It reads the current pressure inside the fuel tank, the ambient temperature, and the exact mass of air flowing into the cylinder. This timeline shows the result of that math: the base pulse width. The computer translates those sensor readings into a precise milligram target, commanding the fuel injector to open for a specific, isolated microsecond. That calculation establishes a baseline for survival. But a human driver's behavior is completely unpredictable, requiring the software to instantly break its own rules. Detecting a sudden demand for speed, the software shifts into power enrichment mode. It ignores efficiency targets, dumping gas into the engine to maximize torque. The opposite occurs when a driver suddenly lifts off the pedal to coast down a hill. This chart plots engine speed against fuel flow during sudden deceleration. The system activates a cutoff, dropping the fuel line to absolute zero. To prevent stalling, the software carefully ramps fuel back in, cylinder by cylinder, just before hitting idle speed. Managing these extremes proves that the system prioritizes dynamic, contextual response over rigid, unchanging rules. Those split-second decisions manage the driver, but the system also has to manage the fuel itself, specifically after the driver leaves a refueling station with a new, unknown batch of gas. The engine doesn't just guess. It initiates a fuel quality index test to determine the exact methane concentration of the new batch. Here, an oxygen sensor scans burned gas molecules flowing toward the tailpipe. By measuring what's left over, the software reverse engineers the fuel's chemical makeup. This data pushes the engine's entire math formula up or down, resetting the baseline for the new fuel grade. The engine adapts to its fuel source independently, without input from a mechanic or driver. Even with perfect fuel, hardware ages. If a vacuum leak develops, it throws off the ratio and causes the engine to run lean, meaning there's too much air and not enough fuel. To counter this, the software uses a long-term memory mechanism called the block learn multiplier, or BLM. This grid represents the engine's speed and load. When a fueling error occurs, the system highlights the exact cell with the imbalance. The BLM permanently rewrites the baseline fuel table for that specific cell, baking a correction factor directly into its memory. By localizing these corrections, the software ensures the engine remains efficient even as it ages, using digital logic to offset physical wear. Back at the macro level, the experience for the driver is flawless. They remain completely unaware of the underlying chaos the computer is navigating. That smooth ride is the result of an invisible symphony, thousands of split-second calculations, adaptations, and corrections happening beneath the hood every single mile. Scaling alternative fuels like CNG for daily use is an achievement of software engineering. The reliability of this fuel source depends on an intelligence that can continuously correct for its own environment. The traditional, rigid mechanical engine is dead. It has been replaced by a living, adapting computer.